24 hours to cure. Then routine testing. Impulse testing is a routine for all bushings above 145 kV. So this is the impulse test setup which we need to have. And this is the AC testing, and here in case of whether it is RIP, RIS or OIP bushings, the main interest is to monitor partial discharge at 1 minute level. And you can see here we have an electromagnetically shielded laboratory. We have to have sensitivity to measure 1 PC or 2 PC like that. So you can see at the bottom a picture of PD meter, where at 1 minute withstand level of 245 kV, the partial discharge is 7 picocoulomb. So it is partial discharge inception pre-bushing. Let's look at long-term reliability aspects, design, material, process and routine evaluation. In OIP insulation, the basic theory, as I learned over my experience, is you need to have thinner oil films. So the paper to oil ratio is typically 90 to 10. 90 is paper, 10 is oil, or below 10 also. And these thin oil layers will have higher dielectric withstand capability. At the bottom what you see is a resin impregnated film or resin impregnated paper. Basically those are loose windings, and which have to have 60% is the paper or film and 40% is resin, because resin is thick, so means it is thicker than, it has got higher viscosity than oil, so it requires more space to penetrate, and we have to achieve partial discharge free performance. This is a famous curve published in one of the cigarette literatures about 50 years back. On various OIP models, they have done, on the y-axis what you see is the PD inception voltage, and on the x-axis what you see is the duration in minutes. So you can see if you have a partial discharge inception free bushing, OIP bushing, it has got an inherent service line. Those two lines are the probability lines, what you are seeing, red and blue lines. In between them, the life will be ensured to be, if you ensure PD inception free OIP bushing. Similarly, this is a graph of resin material which was published by Dr. M. Baer of Switzerland. And there also the life curve is almost similar. Here, in case of resin, the stress withstand capability of resin is higher than oil. OIP, let's say RIP is higher than OIP, but people are still cautious. They still operate at lower and lower stress levels to ensure more reliability. Important aspect is condenser grading. How finely you do the condenser grading, that decides the quality of the bushing. Materials which are used in insulation construction. Most important is the kraft paper, big width kraft paper, what you source. The best of the papers, based on my experience, are manufactured in Europe, which has got lower conductivity of aqueous extract, and those have to be used. Because today at testbed level it may be okay, but for longer life you need to have a reliable paper. There have been cases where the conductivity of aqueous extract of paper has been on the higher side, and the bushing failed after 10 years of service. Materials used for sealing, what is the margin on that? In OIP or RIP and RIS, even if the continuous operating temperature goes to 105, 120 degrees centigrade, but you use white-on-like material which can withstand 160, 170 degrees centigrade continuously. So you build safety margin. Oil compatibility has to be evaluated for all the materials, and which is being regularly done in the industry. And maximize use of O-rings, not gaskets, flat gaskets. And most important aspect, what I have experienced when we used to do R&D in my earlier days, we established that naphthalene-based insulating oil gave us better electrical aging properties when we modeled it on capacitors. Crepe paper. If crepe paper can absorb 6 to 7% moisture, the films are known to absorb less than 0.3% moisture, even if they are exposed to higher humidity for long period of time. And it is a synthetic material, you can make it better than paper. That is the thing. Condenser core winding, it has to be done on machine so that you have higher number of condenser grading coils. As if you can have every turn of paper you insert a grading coil. You have minimum human touch during winding because human perspiration can create a dielectric contamination. You have consistent dimensions are achieved so that the process is really statistically controlled well. And it is a wrinkle and fold free bushing because wrinkles and folds in a winding, they can result into local stresses and it can result into PD issues later on. And it has to be tight winding because you remember the ratio of 90 to 10 of paper to oil. Drying and impregnation, you need to dry it at temperatures more than 100 degrees centigrade. You need to have vacuum finer than 0.1 MBAR on Pirani gauge, not on MacLeod gauge. Oil impregnation has to be based on the capillary rise of, it has to be at a rate lower than capillary rise of the paper. And oils drying and degassing is the most critical aspect according to me. Leak testing, because whatever helium leak testing you do or leak testing under water you do, that establishes the long-term leak proofness of the product. So this is a critical aspect. And ascertaining PD inception pre-performance during routine testing, that is most important. And we have found DFR assessment of OIP bushings particularly to be most effective method of assessing the moisture content in paper insulation, and we are effectively using it. Some few concepts of capacitance tan delta. Sometimes most misunderstood topic, so I am repeating it here. C1 is the part of the bushing between the central electrode and the test tap coil, and C2 is the part which is between the test tap and the mounting flange. C1 is measured in ungrounded specimen test mode, C2 is measured in grounded specimen test mode normally. As we have seen, all the capacitor elements are connected in series. So just imagine that if one particular capacitance segment fails, what happens? There will be change in capacitance. So there is a SIGRE document 755 which has come out in 2019, which talks about percentage change of OIP and RIP bushing. You can consider RIP and RIS as the same. Since RIP or RIS bushings, they need more space for impregnation. You know, the number of condenser grading coils used are lesser. So the change in capacitance for per capacitor element failure or per capacitance segment failure is higher in RIP or RIS. This is a generic guideline given, but the best will be if you follow the manufacturer's guideline. He may say one coil failure is okay, two coil failure is okay. Another aspect of capacitance-based monitoring is capacitance changes with temperature. Please remember it this way. And OIP has got a temperature coefficient of capacitance which is to the tune of 0.025% per degree centigrade, whereas RIP or RIS, RIP has got the highest 0.045 to 0.08% per degree centigrade. Just to give you an example, if the temperature is not corrected to a common temperature, normally people use 20 degrees as the reference temperature. What will happen is just temperature change from 20 to 50 degrees centigrade can change the capacitance value from 500 to 505 picofarads. So while evaluating the change in capacitance, whether it is due to the failure of one capacitor segment, this temperature dependency has to be accounted for. Now tan delta concepts. You know, IEC and IEEE, they have different limits for tan delta value. Some people use tan delta terminology, some people use power factor terminology, but both are more or less the same, below, say, 1% as the tan delta value. In OIP bushing, you will see that the tan delta value is around 0.003 to 0.004. This is at normal ambient temperature, let's say between 10 and 40. RIP bushing, because of intrinsic high losses of resin material, it will be 0.004 to 0.005. There are two parameters which are defining the tan delta values, two physical phenomena. On the leftmost side, what you see is a parallel circuit, which is parallel path to the capacitor. RP is the parallel path to the capacitor, and that we say is a charge flow. And on the right side, what you see is the charge orientation capacitor. So, both these parameters, the main parameter which is contributed here is RPCP in parallel. In OIP, you will see a typical stability of tan delta when the moisture contents are on the lower side. The 0 degrees to 100 degrees centigrade, the tan delta variation will be less than 0.001 absolute value. But whereas in RIP and RIS there is a hockey stick curve. Always you will see that at around 60 degrees centigrade, the tan delta will be lowest in RIP and RIS both. But as the temperature goes lower, the tan delta keeps on increasing. So we have to appreciate this fact while you monitor the tan delta values. Again, this SIGRE document 755 gives the permissible limits, how to monitor bushing condition based on the tan delta increase related to pre-commissioning value. So, in OIP, people say that if the tan delta value at pre-commissioning level was X, if it goes to 2X, you should consider it as a warning and you should immediately take action to remove it out of service. In RIP, tan delta increase is not expected. Still, they say that if it goes beyond 1.76, you should consider
gases. Okay, depending which gas is top, sometimes people talk about key gas. Another extension ratio method is the shape method. So beloved by. So this is a nice simple version of ratio method. This is from IC 60599. 5 gases, 3 ratios. Simple, it's easy to understand. I'm not a chemist, I can understand it, I can apply it. Is it simple and easy to apply, or is it too simple and too easy to apply? Could we get more information out of the results? Most other standards have got more diagnoses. So if I look at extending the ratio method into the shape method, this is from Michel Duval's magnum opus, Segre brochure 771, 3 triangles, 2 pentagons, 10 diagnoses. And you're looking at, okay, the more eagle-eyed amongst you will have noticed you're looking at the 2 pentagons there, and there are additional triangles and additional pentagons for other liquids. Then the first half of my question, which I'm answering second, how do we know what's normal anyway? And that almost becomes a bit of a philosophical point. What do we mean by normal? Is it normal for all the transformers in the world? For all the transformers in India? There are 6 lakhs of distribution transformers in India. Is it normal for my transformers? Or is it normal for that transformer? So IC and Segre, they've done statistical analysis on a lot of data from different utilities, must be said mostly in Europe, and they've come up with some tables for typical dissolved gas levels. IEEE 57.104, based mainly on the US, have come up with a rather more complicated table which I'm showing you. And is this getting a little bit too complicated, a little bit too difficult to apply? Well, I think that might be a matter of opinion. So,
as the editor-in-chief of this green book, I'm trying to give people some guidance. Conflicting interpretation methods are causing problems for many users, especially in case of warranty claims. I had somebody moaning on at me about this last week. It was actually a manufacturer. There's nothing wrong with my transformer, but the customer's found a guide that says there is. I've also seen that problem the other way around. And what I think is that differences between the performance of different oils, different materials, differences in transformer construction, and even differences in operational practices don't really seem to justify the difference between all the different standards and guides. And possibly there's just too many standards and guides. Standards and guides are a good thing, but one recent warranty claim, I believe, they went through 9 standards and guides. And yeah, that's not helpful anymore. So, another question, what is normal? Is this rate of change in dissolved gas levels normal or not? These are genuine results from a genuine online dissolved gas analyzer. I'm not lying to you on the slide this time. So, normal, not normal. You can see this is a transformer. It probably does have a bit of a fault, as it's got over 1,000 ppm of ethylene in it before they degas it and do the internal inspection, where incidentally they don't find anything and they don't fix anything. Then we sort of go back to gassing at the old rate, and then there's a sudden change over a week. And I had the customer on the phone. What do I do? Well, so I referred to the standards and guides, and I might as well not have bothered. The standards and guides out there are very much oriented around lab dissolved gas analysis, where samples are taken at quite long intervals, weeks, months, even years. The results tend to be very accurate. If we look at the case with the dissolved gas analyzer, okay, our Morgan Schaffer dissolved gas analyzers are very accurate, but maybe some of the others aren't quite so good, and a sample is being taken every few hours. How do I respond when the dissolved gas analyzer goes berserk? So please, can we have some guidance on typical rates of change or increase which are adapted to dissolved gas monitoring? forgot to mention this earlier, I apologise. On conflicting interpretation methods, there is actually a C-grade working group looking at this. It's D1A277. And on rates of change, there is another C-grade group looking at this. It's A2D167. So anyone who feels like volunteering, please go to the C-grade website and have a look. Well, Mr. Chorda has certainly been adding to this issue, this new challenge. Transformers immersed in liquids other than oil have been around in small sizes for a long time, I think since the 40s with PCBs. Esters have now been getting a lot more popular, a lot of production both of esters and of ester immersed transformers in India. Getco have got a lot in service, medium sizes, but there's been a pilot project at 400 kV. Other countries are a little bit further down that road. Great Britain and Italy have got dozens of transformers at 400 kV immersed in ester in service. There's also quite a lot Sweden and Germany. China are now building prototypes at 500 kV. If I look, wrong button, and there has been some experimental work done on this, and people have looked at it theoretically. This is from a PhD at the University of Manchester, where they compared jet gas generation in oil and in synthetic ester, which is what they make in Manchester, at different temperatures. And what that's suggesting is you should see roughly the same dissolved gas signature for overheating faults in oil and in ester. Also seems to be the operational experience. What are typical dissolved gas levels? Well, people are a bit vague about that. That's some guidance I could find. That's in a C-grade brochure from 12 years ago, when we were very much dealing with sort of 10, 20 MVA size transformers, not the bigger transformers we see now. And there's actually a fairly small number of transformers in the study. So I think this needs an update, and I would like something that has a similar look and feel to the standards and guides for oil. I don't really see why we need to reinvent the wheel about what the standard and guide should look like and the process we should follow, but maybe we need to look at different ratios or different limits for the diagnoses or different limits for what's normal and what's not normal. Okay, artificial intelligence. I said earlier I had 5 years in SFRA, and towards the end of that time we were trying to use artificial intelligence for interpreting SFRA results. That was more than 20 years ago. A very interesting publication came out a couple of years ago by Patrick Pichet and his friends. Other people are still trying to do that. I hope they're getting a bit further than I managed. There is, we think, a lot of potential in applying some of the new techniques in artificial intelligence and machine learning to transformer condition assessment. And we think it's especially high in understanding the correlation between the findings of different condition assessment techniques, which is an area where we haven't made so much progress so far. So this is a most interesting paper on this subject. It's by Louise Heim, who's one of the co-editors of the Green Book. He's got some very interesting ideas in that need following up. And a little bit more about the why. I think we've heard a bit about this already. We already have 6 lakhs of transformers in India. In 10 years, that's going to be a lot more than 6 lakhs. We're managing more transformers than ever before. The average age is going up, and yet the number of engineers is not going up as fast as the number of transformers. Sourcing transformers is getting more difficult, sourcing replacements. Even in emerging market countries, it's getting more difficult. So we're very fortunate that we got all these wonderful new condition assessment techniques, all these wonderful monitoring techniques, but we now need to get the computers to do a bit more of the hard work for us. So before I conclude, I would like to thank all of the contributing authors to the Seagrey Handbook, because most of this, I'm afraid, is their material, not mine. And I would especially like to thank the co-editors. That's Louise Heim, who I mentioned earlier, Tara Lee MacArthur from Australia, and Mr. Adish Gupta from the Power Grid Corporation. I hope I've not made everybody too late for lunch. Thank you.
Thank you, Mr. Simon. Now I request Sumit sir, please present your presentation.
You have a question?
Can I ask a question, please? Do we have standardization of gas percentage or any ratio against the fault type? Or if it is there, then why we are only indicating the percentage of gas on an instrument which is continuously monitoring the dissolved gas fitted at the transformer? It is just showing the percentage of gas, rather showing fault type. If it can shows the fault type, the user at the end will beneficial more, I think. So if there any kind of a standardization of table which can say that if there is a this kind of gas, then there is a fault.
There are indeed many standards and guides on that subject. Indeed, possibly our problem isn't that there aren't, is that there are too many rather than not enough, and that they don't always agree. So this is something I think we need to do some more work to improve the standards and the guides, and above all to get more uniform diagnoses across them.
That means currently it is not fully standardized.
Standards are a wonderful thing. Everyone should have one.
Okay, thank you.
Okay. Yes, now I request Mr. Sumit to please go ahead.
Good afternoon, all of you. This is Sumit Sharma from Skipper Sail Limited. Actually, I am here to present one practical situation. Okay. Now, am I audible? Yeah, thank you. Just like in case of OLTCs is a kind of thing, very interesting thing. So, as in we are talking about the transformer, so we are using mainly two type of OLTCs, the linear type OLTC and the reversing type OLTC. It may be single or maybe double type. Then the course and course windings will come under the picture. This is just a different issue. So here I am just discussing about the single phase reversing OLTC with the DM box operation. So maybe on the sites, many people observed that on the DM boxes or maybe on the fan control cubicles, you find some insulations over there. Maybe the fiberglass insulation or maybe some tube type insulations are there. So we are just trying to touch a reason that why it is provided. There could be a possibilities that why it is provided. There are a number of possibilities, but here we are discussing maybe one of them. Okay. So the subject is tripping in DM box of single reversing changeover selector type OLTC while rotating during open circuit test. Actually, it is a situation which is demonstrated in the test laboratory while performing the testing on the transformers. As per standard, we need to rotate the transformer at its rated voltage. Maybe, just like if I will take the example, the transformer is 132 by 33 kV, then we need to inject the voltage 33 kV from the secondary side, and we need to rotate one complete cycle of the OLTC from the maximum tap to the lowest tap. So this is the scenario what we are discussing. So these are the contents which I am covering. Let's go directly to the content. So single reversing changeover selector switch. It is just this reversing switch, the requirement of the tapping winding. Just like if we want to add the tapping winding in the main circuit, then there is two possibilities. The first one is the linear type, which will take the complete all 17 taps from the winding and it will connect it one by one. This is the single scenario. And in the second scenario, just like here in the reversing, it gives us the opportunity to provide 9 number of taps and then it will rotate it in the one direction and then in the other direction. So during the operation, there is a point where the tapping winding is disconnected from the system completely. And on that time, what will happen? On that time, the discharges will happen with the tap switch, because the voltage which is occurring when the one winding is disconnected from the circuit, then the reverse voltage will come over there, which we called as recovery voltage. Okay. However, it is controlled through the tie-in registers with many other things, but in that situation also it happens that the discharge will happen on the with the selector switch itself. So this is the same thing which I have already told. Actually, there is some shortage of time, that's why I am not repeating all these things. So this is a general method how we can control that recovery voltage. It can be controlled through a tiny register. It is just a normal practice. In many transformers, people are using that. So here. So now, this is the thing. Here one small diagram was shown. I think. Okay, let it be. Here on the diagram, you can see in this scenario, presently the OLTC is connected to the point number 4. Means OLTC is in the one direction, it is moving. When it will be connected on the 12 position, then the direction of winding will become reversed. Okay. So in this situation, what is happening when we are when we do the testing? On that time, what is happening when the connection and disconnections are happening? On that time, due to that recovery voltage, which is coming while operation of the OLTC, connection and disconnection of the tapping winding, the extra voltage will be generated and that will be discharged through the tap selector. And when it will be discharged through the tap selector, then that voltage will come to your DM box, drive motor mechanism box, and there itself, due to that discharges, your main MCB protection circuit and your overload relay, sometimes people also said that MCCB, okay, that got tripped because the level of discharge for that fraction of time will be higher. And in some cases, you can imagine that the level of that faults is like that, it may damage the motor also, which is responsible for rotating the complete shaft or the complete OLTC. So after completion or after identification of this problem, how it can be solved? So it is as simple as that possible. If you want to ground something or if you want to eliminate anything, any discharges, then you need to ground it directly. Okay. So in that situation, the transformer is grounded, but your OLTC is also grounded with the transformer. Your DM box is also grounded with the transformer. That you need to separate because the surges are coming through the tank body to your OLTC. So same thing was happened here also. So we have just removed the direct connection and provided an insulation between both of them. And then it will be tested and it will be confirmed. So this is my presentation. Thank you.
Thank you for very short presentation. Now in this session, we have covered 3 important topics. First, bushing, and then DGA monitoring, and then last, the tap changer. Okay. So the last presentation is covered very short time. So we have sufficient time for question answer. So we take some question. Please introduce first yourself and ask the question.
My name is Sanjeev Kumar. I am from Torrent Power. So basically, nowadays we are going with all SF6 to oil bushings. In that case, what is happening is that once the bushing is installed with SF6 duct, in that case, some of the OEM, means I mean to say the transformer manufacturers, they say that if we don't do 10 delta regular basis, it is okay. But some of the OEMs say that you have to do the 10 delta regularly. The problem is that the SF6 module, which is fixed on the bushings, we don't have access to this 10 delta. So because if we want to do the 10 delta on regular basis, we have to do the degassing, then vacuuming, then it is a lengthy process basically, because 10 delta tap point is coming out of that bushing. So what is your advice, whether this 10 delta has to be done regular basis, or the quality of gas, if it is okay, whether we can continue without doing the 10 delta?
Actually, this needs a detailed discussion. Can we do it during lunchtime or during the day?
Yeah, definitely.
Yeah.
Thank you.
Hello. Hello. Yes. So, question to Purvendra-ji. Hello. Question to you, sir. You very nicely explained all the type of bushing, OIP, RIP, and then synthetic RES. Then my question is, should we write off OIP bushing the way it is progressing? My question is that so much technology has involved, so much measurement techniques have involved, so much technology of making OIP bushing has improved, and we are doing it. So what is your viewpoint, that should we write off OIP, or what should be advice to the people based on the cost and availability and the technology and the integrity of the bushing?
OIP, as you have said, it is a mature technology. So my take is, because I belong to OIP generation, let me say that. So I will always prefer to use OIP with high reliability concept. But when you look at usage on the transformer, definitely utilities are mainly concentrating on preventing the transformer failure. If OIP bushings with good online monitoring, it can help. That is the right solution if OIP has to be used. But I believe OIP is going to stay. But RIP and RIS are going to catch up, and they will exceed the OIP business per se. OIP is not going to vanish. We cannot write it off that easily. Because still, the main dilemma of the users, as I have found, is that they are still having more than 60% of the bushings. Even developed utilities like TNB Malaysia, they still have 50 to 60% bushings of OIP yet to be replaced. Because replacing a bushing is also a task in a country where the power demand is on the higher side. So, according to me, OIP is going to stay. We are exploring usage of synthetic ester or natural ester on OIP platform. EIP, what Trench has called it as EIP. We are exploring that, but maybe it will take another couple of years for it to establish. Because it has come into the marketplace through one manufacturer and just about 2 years back. But till that time, OIP with mineral oil is going to continue, according to me, but may not be at high pace. That's what I would say. And cost is a decision. So you know, as a transformer user, what you will value the most. Thank you.
Hello. Sir, my question is, myself Manish Pandya, I am from MACPL Baroda. When one of the participants has raised the question about the 10 delta test step problem, and we are also facing the same. So just my question is, can't we standardize the test step? Because every manufacturer has their own design, and as a service provider at site, we face the multiple problem with the multiple type of the test step. So the connecting the multiple type, it needs some kind of a separate literacy. So can't we make a standardized, like even a mobile phone has now standardized this charger. So if it is possible.
Yeah, yeah. Actually, you have raised a very valid question. And standardization of bushing test tab is a topic which is taken up by IEC standard. And there is a committee which is working on it right now. And they are working on the topic of standardizing the test tab terminal sizes, the threading sizes, so that the change which will happen is only the earthing of through the cap. But the basic concept for adopting online monitors, that is getting resolved. I hope in next 1 to 2 years time it will be resolved. I am a part of that committee on BIS on that.
All right,
We
sir.
are
Thank you.
working on
Thank you,
it.
sir.
Thank you.
Hello. Yeah. Myself, Pranay Joshi. I am from MP Transco. My first question is Mr. Rao. During the measurement of 10 delta of bushing, sometimes the negative value of 10 delta comes. Sometime during the 10 delta measurement of bushing, negative value of 10 delta is come.
Correct.
So what is the reason behind this?
Can my presentation be again projected? Because I can explain it in 2 minutes.
Okay. So once the presentation done, one more question with Mr. Simon. Once the presentation is come.
No, till that, just
Okay.
hold on.
Okay. By the time, can I ask question with Mr. Simon? Once the okay, no. Sir. Okay, Mr. Simon, can I ask question?
Please go ahead.
Yeah, as you say, we are using artificial intelligence for interpreting the results of DGA analysis nowadays. We can use the artificial intelligence for interpreting the result of DGA.
We can, yes. It's been around, that's been around for about 30 years.
Around 30 years it requires, sir.
Yep. I think there was a paper about it from the early 90s from the US. I know for a fact that CG Research in Mumbai also did some work on applying artificial intelligence to DGA.
Sir, because nowadays the online monitoring devices are there, they are only showing the percentage of gases in the oil. They are indicating that the acetylene is increasing or methane is increasing. Can it be possible at the real time they can interpret us ki what was the going between the inside the transformer, why they are increasing? Just like the DGA test result, they are interpreting, giving the interpretation that there is a hot spot, there is a fault of movement greater than 3 degrees centigrade.
Can we look? I mean, is it possible for? For the online gas analyzer to give an interpretation of the results in real time? Yes, it is.
Yeah.
There's certainly software available that will do that and will work across different platforms. I don't want to give a plug for my company, but we certainly have such software, so please talk to my colleagues.
Okay, thank you. Yeah, Mr. Rao.
They're sat right next to you. Okay. Mr. Rao, I think.
Okay. Now this is the last question. After that, we proceed for the lunch and requested to all the participants, please quickly return from the lunch. So we are already delay half an hour. Okay, thank you.
Just a moment. तो slide खोल रहा है?
No. Okay. Till I try to give answer of your question, why 10 delta is negative? There is a one reason. Your equipment is not properly earthed. Means it is not at zero potential. This is the one of the reason. The second reason is there is a parallel path. Okay. So there is a two main reason, and Pramod sir will explain this reason in diagram. Okay. So we notice negative 10 delta, particularly in case of CVT, capacitive voltage transformer. When we measure the 10 delta, it is always negative. Okay, go ahead, Pramod sir.
As you can see, as you ca- as you can see in this figure, when we talk about negative tan delta, by theory, it means that the tan delta value means the resistive current has to be on the negative side because it is IR by IC, ultimately IR by IT, what you can say. So this is the definition, let's say that. Okay. Now let's look at the concept that when you have Z1, Z1 is nothing but C1 capacitance. Okay. And Z2 can be considered C2 capacitance. Okay. But just imagine that our Z2 was part of C2 and part of C1. So somewhere the current which is going to go to the bridge is bypassed through that EG level there, and it is getting bypassed through a parallel path to ground, and it is not passing through the bridge. So as a result, what happens is whatever is the phase of the current which is passing through the bridge, it changes. There is a very nice explanation of by Doble team. They have done experimentation. There is a specific technical paper. I can share it with you. When you share your address with me, I will share it with you. And the parallel path actually makes the tan delta negative. Now, where does the parallel path come? Now, the parallel path can be external to the bushing, or there could be an internal damage. That is, there is a parallel path, there is a tracking somewhere. Can you go back? Go back. नहीं हो रहा है, नहीं हो रहा है, नहीं काम नहीं करता है. नहीं, go back. Yes, stay there. Just see this figure. If there is a grounded layer, okay, what you can see there, grounded layer or grounded flange. Just imagine that there is a contamination deposited internal to the bushing in this path. So this is a current which is going to the mounting flange ultimately at a mid potential level. It is not at test tap level. It is somewhere from in between the current is passing to ground. When it is happening like that, it changes the path. It changes the phase of the current related to voltage which is passing through the. There is a very nice mathematical explanation to this also given by Doble team, and they have done experimentation on that. It is way back published in 2002, and it was again experimentally proven by one expert from Western Australia. Great. So there are two technical papers on the subject. You can share your contacts with me. I will share it with you. Thank you.
Okay, thank you, Pramod sir. Thank you, Sumit sir and to Ms. Simon for nicely explain their subject and nicely answer the question also. So now,
Yep.
proceed.
So, thank you so much for the session. Please be seated. Don't be get up. We still have last 2 minutes session, and I request the session chair to felicitate authors. So, may we start with Simon. Thank you, Chairman sir. Chairman sir, be there only. Mr. Pramod Rao, please. Thank you. And Mr. Sumit, please. Thank you, thank you. May I request Mr. Negi sir to be on dais to felicitate our chairman, please. So this is going to be a unique coincidence, sir. Thank you, Chairman, for timely managing the session and taking in depth to the three subjects. To the Chairman, yep. Yep. Thank you so much. Negi sir, be there. We will have a group photograph on the dais. Please be there only.
लकी ड्रॉ रेडी है लकी ड्रॉ रेडी है
लकी ड्रॉ रेडी है अभी कर सकते हैं ना पहला
Thank you, thank you, thank you. Be there. Okay, we have one small input to all. As many of us know, the industry veteran, our friend and guide, philosopher, Shri Jitendra Mamtaraji has joined late, so morning we could not greet him. So may I request Jitendra Mamtara to say hello to everyone? Mamtara sahab.
Good afternoon, everyone. And sorry I missed out the morning session. My flight got delayed. In fact, I decided to join this conference only late in the evening yesterday, 9:30. I was not to come, but then I decided Mr. Negi was very insistent that I should come and join. Thank you very much, and I hope you will enjoy your lunch. Thank you.
Thank you, sir. Okay, we have one session before we break for lunch. One moment, don't be again. So this is a small last session which will really improve on your hunger, and then next session can have a good sleep. So this is a small lucky draw from the participants. So I'm sure 99% participants are covered. So priority goes with the female member. So our experts will go to the female members first and pick any of this one. Yes, hand it over to you, sir.
Hello.
Sorry.
लकी तो हम सब हैं क्योंकि इस शानदार इवेंट में हम सब एक साथ बैठे हैं, लेकिन फिर भी मुझे ऐसा लगता है कि और भी कुछ लोग होंगे जो बहुत ज़्यादा भाग्यशाली हैं। तो ऐसे भाग्यशाली लोगों को ढूंढने के लिए मैडम एक थोड़ा आराम से निकालिएगा, एकदम ऊपर से नहीं मैडम, अच्छा ऊपर का, ओके मैडम। तीन नीचे हैं प्लीज, इसको रखिए 2 मिनट है ना जी। मैं बता रहा हूँ उसका क्या करना है। इधर सर प्लीज एक, जैसी आपकी मर्जी। 3, थोड़ा इधर भी आ जाता हूँ सर। 4 सर प्लीज। अब देखना ये है सर कि लकी कौन है। तो सबसे पहले मैं जिनके पास गया था, पलक मैडम रखिएगा इसको रखिएगा। मैडम नंबर क्या है आपके पास में? 7178। मुझे उम्मीद है कि आप लोगों के पास में जो बैचेस दिए गए हैं उसमें ये नंबर किसी के पास लिखा हुआ है। 7178 है कोई लकी? 7178। ओहो, थोड़ा सा चूक गया सर। 7178, हाथ ऊपर करेंगे प्लीज। ओके, चलिए एक लकी ड्रॉ भी आप और निकालिएगा, इसको रखिए मैडम। 7193, 7193। ओहो, पहले लकी, तालियां हो जाए जोरदार। मैडम वो उन्हीं को दे देता हूं। सर 7193 ये आप रखिएगा प्लीज। यहां से एक लिए हैं सर प्लीज। 7102, 7102। ओहो, लकी 2। हाँ जी सर, थोड़ा हाथ उठा लेंगे प्लीज, तालियां बजनी चाहिए, भूख और तेजी से लगेगी। मैं आ रहा हूं थोड़ी देर से जी। इसके बाद और किनका है कूपन? आपके पास है ना सर? जी मैं आ रहा हूं आपके पास में। सेवन 7099 सर, ये भी शायद तक कोई है क्या? 7099। इसको 2 मिनट पकड़िए, अभी आप एक और निकालिएगा। और एक किसी को दिया था यहाँ पे सर प्लीज। सेवन वन फाइव। आगे क्या हो सकता है? 7156। एक नंबर से आप खुद ही चूक गए। मतलब सर लकी की भी अति होती है ना जी। 7156 कोई है? चलिए हमारे पास 3 लकी और हैं, तो 3 अभी लकी जो है वो इधर उधर हो गए, तो 3 और लकी विनर्स के लिए बोल दीजिएगा मैडम। हाँ जी मैडम, मैडम नीचे से ऊपर में एक एक नंबर आ रहे हैं जी। हाँ जी मैडम। 7192। ओहो सर आइए, 3rd। थैंक यू मैडम। तालियां बजनी चाहिए, भूख बढ़ते जाएगी। इसको थोड़ा संभाल के रखिए मैडम। एक निकालिए आप लोग, थोड़ा नीचे से निकालिए मैडम। सेवन 0 3। उसके बाद किसने कहा 7? सर सही निकल गया, 7037। सर आप हाउसिंग, आप ओह ओह पीछे हैं, पीछे हैं। सर ऐसा होता है कि हाउसिंग में जिसको अपना नंबर चाहिए है वो बोलता है। वहां 2 लोगों ने 7 बोला, यहां से आपने बोला। सर बधाई हो, इसको थोड़ा रखेंगे। 4 एक और बचा हुआ है, मैं इधर बीच में आता हूं सर प्लीज। एक 5वां नंबर निकालेंगे। 718। देन नहीं, 5 नहीं है। 718। 2 भी नहीं है, 3 भी नहीं है, 0 तो नहीं है। 4 7184। ये नंबर भी मिसिंग है। तो अब यहाँ पे इस प्रोग्राम को रोका जा रहा है। जिन 4 लोगों के पास में उनके नंबर की चिट है, उनको क्या करना है आगे से इंस्ट्रक्शन आ रहा है प्लीज। थैंक यू वेरी मच।
Thank you. So all these 4 winners, please come front. All these 4 winners, please come front. you are going to be more lucky than this cheat. Please come forward. I can't see. 1, 2, where are others? 3 and 4. And you are going to get a fantastic gift from none other than Shri Rajamani sir. Okay, and you are going to have a lucky picture of your life with him. So Rajamani sir, please. Take a picture. सर आपका नाम और आपका ऑर्गेनाइजेशन बताइए.
So myself, Radha Manohar. I came from Power Grid Corporation of India Limited.
Wonderful. So PGCL as usual took a first most luckiest guy. Okay, who is the second? All right.
Sir, my name is Hardik Singh Jadeja. I am from Onnet Transformers Private Limited.
Say it again.
Onnet Transformers Private Limited.
Perfect. Now the transformer manufacturer. The third one.
Myself, Rajat Goel. I am from PGCL.
PGCL has taken two. Thank you. Where is the fourth? Oh, thank you.
Myself, Santosh Kumar. I am from Old Time Transformers Limited.
Wonderful. Whole time India, right? Perfect. So we have 2 OEM and 2 from utility. Please, sir. So thank you so much and enjoy your gift. Now the session 2 is officially over here. We go for the lunch. There is a veg and non-veg separate counter, so people can have either of their choice or both of the food. And we reassemble here in 40 minutes. Is 40 minutes enough? So that means at 2:35 we will be back in the hall. 2:35.
Oh. Check, hold. Hold, check, hold.